Hey everybody, welcome. This is section 3.8 and we are talking about the centroid. Sounds impressive, doesn't it? Well, we're going to take a look at what the centroid is and what special characteristics it has. Alright, so on this slide I have a scalene triangle CNR, and I'm going to construct the centroid. By definition, the centroid is the intersection of the medians. So let me say this up here. The centroid, it's the point of concurrency, right? We define this in the notes. Point of concurrency of the medians. So a point of concurrency is the point where they all intersect. And in this case, the point where all the medians intersect is the centroid. So we're going to construct the centroid. So we have to find the midpoint of each side. So we need to construct some perpendicular bisectors to find those midpoints. So this should, be a review for sure. I'm just going to kind of go through it quickly, hopefully. Putting my compass more than halfway on each of these, striking those arcs. And, oh, wait a second. Let me go back here. Take that back. We'll go up here, right? There, and there. And now we'll flip it around and go over here, and there. Uh-oh. Come on down here. And there. So now I can see that my midpoint is right there. So there's one midpoint. So let me make that a little bit smaller. I'll just use a dot right there. There we go. That's better. I like that. Now I'll come over to side CR and find its midpoint by constructing perpendicular bisector. It's going to be a little bit crazy. There we go. Bring it over here. Oh, looks like I'm going to need to go back and do that other arc again. Need to extend this a little bit more so that it intersects. There we go. And that will come up here and construct, there we go, that perpendicular bisector by connecting this to that. And now I have the midpoint of CR to be right there. Now I need the midpoint of NR. It's going to get a little bit crazy. I'm going off the page, but it's going to work out right here. There we go. So there's the perpendicular bisector. Move this over a little bit. There we go, perpendicular bisector of NR. So there's my midpoint right there. Now I'm just going to clean up some of this by getting rid of some of these arcs. Let's see how this works. Delete. I don't want to get rid of the point, I want to get rid of the arcs. Okay, so I've cleaned that up a little bit. Let's move this guy out of the way. There we go. And now I can actually construct the medians. So from C to this midpoint, from R to this midpoint, and from N to this midpoint. And now, look what happens. The three medians intersect at the same point. That's why we define the centroid as a point of concurrency. And the centroid would be this point right here, right? So now what characteristics does that centroid have? Well, let's examine it a little bit. All right, so I've cleaned up some things, taken some marks away, and now I'm going to actually construct a ray down here with my straight edge. Because what I'm going to do is I'm going to examine the relationship of each of these medians. So take a look at this. It's kind of interesting. So I'm going from the vertex out to the centroid. And let's see if I can get any closer than that. There we go. So there's my distance. Now I come down here, and I'm going to duplicate that distance right on my ray. There it is. Okay. Now I'm going to come back up here, and I'm going to go from the centroid to the midpoint. And let's see, this is going to be a little bit hard because that goes off the page. Let me swing it around here. So let me go from the midpoint out to the centroid. And now I have that distance. It's not going to give it to me perfectly. I'm going to go right there. And so let's come down here with my compass and let me mark this. Remember, it wasn't exact, but it's pretty close right there. So now the relationship there, it looks like the distance from the midpoint to the centroid is half the distance from the vertex to the centroid. But I better double check this. So let me see here. Let me take my compass and construct the perpendicular bisector of this segment. So I'm going to come up here, strike an arc, flip that over, come over here, strike an arc, and now I can adjust this a little bit. I'm going to do both my arcs above the line. There we go. And remember that my compass wasn't exact on the one, but if I put this right through there, look at that. It's perfect. Well, almost perfect, right? So what we're seeing here is the distance. Remember, this distance was from the midpoint, I'll do M to the centroid. And this distance was from the vertex to the centroid. And so what we're seeing is the midpoint to the centroid is half the distance of the vertex to the centroid. And we could do this with the other two medians and see the same thing. So let's sort of summarize all this together. We defined the centroid as the point of concurrency of the three medians, and I showed you how to construct it. And here we have a new diagram, triangle ABC, with the centroid. And then we investigated a certain characteristic, which becomes the centroid conjecture. It states that the centroid divides each median into two parts so that the distance from the centroid to the vertex is twice the distance from the centroid to the midpoint of the opposite side. So here we have an example of a problem where we would use our understanding of the centroid to solve. So we are given triangle ACT and points S, O, and U, which are the midpoints of the sides, and M, which is the centroid. We were told that CM equals 16, MO is 10, and TS is 21. So let's label CM is 16, see if I can squeeze it in here, 16, MO is 10, and TS is 21. TS, the whole thing is 21. I'm just going to put the 21 out here. We have to remember that it's for the whole thing, TS. So now they're asking us, what is AM? So AM, the distance from A to M, well, we know, and that's this distance, right? We know that that distance is going to be twice as long as the distance from M to O. So if M to O is 10, then AM has to be 20, right? So AM is 20. Perfect. Now SM, they're asking us the distance of SM. Well, we know that ST is 21, and that TM has to be twice as long as SM. So that means that 21 divided by 3 would be 7, right? And so TM would be 14 and SM would be 7, because TM has to be twice as long. So SM is 7. Then we go on to TM. Well, we just found TM. TM is 14. And UM right here is going to be half of CM, so UM is 8. Right? So there's an example of how taking what we know about the centroid, we can apply it to a certain problem to solve. Now here's another very interesting characteristic of the centroid. You know, oftentimes students will say the center of a triangle. Well, by definition, a triangle doesn't have a center, right? A circle has a center, but a triangle does not. But probably the closest thing to the center of a triangle is the centroid. And we call this the balancing point of a triangle, is its center of gravity. And you can see the girl in this picture, she is balancing that triangle on her pencil by placing her pencil on the centroid because it's the center of gravity. Now this idea of the center of gravity has some real life connection in science. It says here in physics, the center of gravity of an object is an imaginary point where the total weight is concentrated. The center of gravity of a tennis ball, for example, would be in the hollow part, not in the actual material of the ball. The idea is useful in designing structures as complicated as bridges or as simple as furniture. Where is the center of gravity of the human body? We can see in the picture that this is a high jumper, right? Probably in the Olympics. He looks like he might have an Olympic uniform on. And the center of gravity, as you would probably guess, would be in his torso, probably right around his waist. So, we have now discovered some special properties of 3 of the 4 points of concurrency. The incenter is the center of an inscribed circle. The circumcenter is the center of a circumscribed circle. And the centroid is the center of gravity. And you can see in this diagram below that it's showing you each of those points of concurrency. we have the circumcenter, which is right here, and it's the center of the circumscribed circle, the circle that goes around the outside of the triangle. It touches each vertex one time. Then we have the incenter here, which is the center of the inscribed circle, which intersects each side of the triangle at exactly one point. And then finally, what we just talked about was the centroid, which we know is the intersection of the three medians and is the center of gravity of the triangle.